Good evening, students. My name is Shashank Shekhar, and we are doing a crash course on the upcoming JEE exam. And today is our 38th day. So we have started the unit that is carbon compound containing oxygen. So we have completed that alcohol, phenol, and ether. So this is the chapter that we are dealing with. Okay. So let us see the topics that are given according to the JEE syllabus. So we have completed this one, this thing. We have completed all of this. Now today we will move to aldehyde and ketone. So we'll start with the preparations today. So these are the methods. We will be using various methods to do the preparation of aldehyde and ketone. And tomorrow we will be covering the reactivity part of this aldehyde and ketone. So let us start our today's lecture. So before starting that, let us see the topics in a more brief way. So it includes the structure of carbonyl compound. Then we will see the oxidation of alcohol for the preparation of the carbonyl compound. Then from hydrocarbons, and then from nitriles, and again aldehyde from nitriles, okay, from hydrocarbon. Then we will see the preparation of ketone also. Then we will move to their physical properties. First one will be boiling point and second one will be solubility. So this is the weightage. You have seen it earlier also. At average of one question comes which is of 4 marks from this chapter. So let us start with the structure of carbonyl compound. So here is the carbonyl compound that we are having. A carbon is attached to double bond O here. If you look at the molecular level, so since we are having an sp2 hybridized carbon here, because we know that since it is forming one double bond and two single bonds, so it will be sp2 hybridized. And this p and p orbital will be forming the pi bond with each other by side-on overlap, and this kind of cloud, electron cloud, will be formed. Now you can see very clearly here one thing that is to be noticed, that this molecular orbital, or you can say the on the side-on side overlap on this p orbital, you can see that the pi electrons are more on the O side because the density is increased on this O side. This is due to the greater electronegativity of this oxygen atom. So this is the part that is greater as compared to this one, which is smaller. So it depicts that the oxygen electron cloud is more towards the oxygen than the carbon due to greater electronegativity of oxygen. Now next, it has a bond angle of approximately 120 degree, each of this angle from C to O, and C to O means CO bond degree, you can say. So let us see some points here. First point is that it is polar in nature. We can see very clearly. So upon conjugation, so suppose this bond go like this, and we can have this form also. This is the resonance structure of this carbanion only. Now you can see charge is developed on carbon, positive charge, and a unit positive charge or negative charge on oxygen. So due to this nature, we have a dipole moment like this from positive to negative. Then this polarity is attributed to the resonance structure B, yeah, because this is the structure that is attributing the polarity most of the time. Then carbonyl compound is an electrophile. Okay, the carbonyl carbon is an electrophile. So why it is an electrophile? Because the electron density is less on this carbon. So this is can be seen from the pi electron cloud, which is less on the carbon side. So it has a, you can say it has an electron deficiency as compared to the oxygen. So it will act as an electrophile. That means it will accept electron, and something which accepts electron is also a Lewis acid. Now second, the carbonyl oxygen, this oxygen, the carbonyl oxygen, will act as a nucleophile because it has a greater density of electrons here. So it will act as a Lewis base. Yeah. So these are the basic you can say definition of acid and bases from Lewis acid and Lewis base. So something which donates electron is a base, Lewis base, and something which accepts electron is a Lewis acid. So oxygen is a Lewis base and carbon is a Lewis acid in case of carbonyl. Now this was all about the structure. So we will next move toward the preparation of this, say, aldehyde and ketone. So using primary alcohol, so we have seen this thing earlier also, so I am just giving a revision to it. So using primary alcohol, so if we have KMnO4 or K2Cr2O7 or CrO3, then we can oxidize this primary alcohol first to aldehyde, then on further oxidation we get the carboxylic acid. Then if you have secondary, say secondary ketone, secondary alcohol, then we can oxidize this using KMnO4, K2RT say it's 7 and CrO3 to ketone. Now it will not be further oxidized to your carboxylic acid because it requires the breaking of CC bond, which is very difficult for any oxidizing agent. Of course, it can happen. The next example is of that only. So suppose we have a tertiary alcohol, and if we want that, we need a oxidation method. Okay, see, we what to do? We have to oxidize this tertiary alcohol. Now, if you look at the structure of the tertiary alcohol, so this is the structure of tertiary alcohol. Now, suppose it is attached to some group. So, if you consider this center here, this one, this carbon attached to 3 carbon. Now, if you have to oxidize it, you have to remove this hydrogen, of course, and make a double bond with O. Now, to do this, since carbon can make only 4 bonds at maximum, you have to break this bond, or you have to break this bond, or you have to break this one. So out of any three, we have to break one so that carbon can make bond with this oxygen. And the main tricky part is that only, means it is very difficult to break a carbon-carbon bond since it is very stable. So what we do, we take an strong oxidizing agent like KMnO4 plus we add some temperature also. So we take some elevated temperature so that CC cleavage take place to form carboxylic acid. So this is the about tertiary alcohol. Now let us see a more interesting oxidizing agent, which is PCC. So here we have the PCC. So what is unique about this PCC? So if you see other oxidizing agent, they are much more means strong oxidizing agent. So if you want to just convert an alcohol into an aldehyde and ketone and stop there, or you can say as approximately aldehyde because ketone cannot be oxidized that easily. So if you want to just oxidize a primary alcohol to a ketone, aldehyde and stop there, so you must need a mild oxidizing agent. So one of these is PCC, so it is a very useful reagent, oxidizing reagent. So it is a mild one, mild oxidizing agent. So it just converts this say primary alcohol into aldehyde. Or you can also say that it is an allylic alcohol also. So you can convert this allylic also to this aldehyde. So this was all about the oxidation of alcohol. Now next, let us move to another method of preparation of aldehyde and ketone. So we have seen this method earlier also. So it is dehydrogenation of alcohol. So what we do is we take an alcohol. So this is the example of primary alcohol, example of secondary alcohol, and this is the example of tertiary alcohol. So tertiary alcohol cannot be prepared, means tertiary alcohol cannot be used for this process to convert it into aldehyde because it gives alkene. So it can be only used for primary and secondary alcohol to convert into aldehyde and ketone. So if we take a primary alcohol and we take the copper surface. So what does copper does here? So it just provides the surface for the reaction so that the reaction takes place easily due to the surface phenomena. Similarly, if you have a secondary alcohol, we do take the copper and at 573 Kelvin, so it is a very high temperature, and we get the ketone here. So if you have to look at the way it is done, so it is a very complex method. So I have just put up a picture here to show how it is done. So this copper we have is supported upon a complex. Okay, so this is CuZn. You don't have to worry about it. I'm just showing the way it is done. So it says that the copper is not included in the reaction. It is just providing the surface for the reaction to take place. So we take a primary alcohol here and we take at high temperature, that is 573 Kelvin, and we do get this aldehyde, which is methane ethane. Okay, so this is ethanaldehyde. So this is the method of preparation of aldehyde or ketone using the dehydrogenation of alcohol. Now next, we can do it from the hydrocarbons also. So when we are studying hydrocarbons, alkenes, alkanes and alkynes, we have seen this reaction earlier also. So what we are taking here basically is that we are taking HgSO4 and H2SO4. So in presence of acid. So this is the reaction that we are having. So we are taking an alkyne in the presence of water. Then Hg2 plus and HH plus, we reduce this thing into an alkene. Now since we know that enol form is not stable, so this enol form is not much stable, most of the equilibrium will shift toward this. Okay, so we can write here also, this is the enol form, so it goes to the ketol form. So this is about this hydration of alkynes. Now if you want to know the mechanism, it happens like this. So this is the alkyne that we have here. Now Hg2 plus will form an intermediate like this, because this alkyne has electron density, pi electron density. It will form an intermediate which will look like this. So let me draw it with a different one. Now what will happen, that we have a H2O. Okay, so this H2O that we are having, now due to the removal of this electron here to this Hg2 plus, we kind of create a nucleophilic center for this oxygen to attack. Okay, so this is kind of supporting actor here. So now the electron of this oxygen can attack here. Okay, and we have a H plus also. Now this is kind of concerted one. So at one step, one of the means the bonded electron, this pi electron will take this H here. Now proton abstraction will take place and we will get this one which is written here. Okay, now isomerization, or you can say, since keto form is more stable than the enol form in most of the cases, so we will get a aldehyde. Now the second method that we are having here is ozonolysis of alkene. So this is a very important method. These questions are often asked here from this part. So this is a kind of reductive ozonolysis. So we can have two ways. So first is oxidative. So we will use that oxidative to prepare carboxylic acid. So since we need a lower oxidized carbon, so we are using this reductive one. So what we are doing is we are taking an ozone molecule here. So first of all, this pi electron will act as a say nucleophile, so it will attack on this oxygen, and it will happen in one step. So it is a kind of conjugated reaction, or you can say concerted reaction. Concerted reaction. So this concerted reaction is not much emphasized on this say 12th part or JEE part, but it is a part of most of the reaction. So most of the reaction takes place to this concerted mechanism. So in one step only, means it does not happen like this. This first is double bond will go, then this electron density will move, and then this will attack here. It happens in one step only, and we get this kind of intermediate. Now since it is not stable, as you can see very clearly, because it is not obvious for the oxygen to form this kind of bonding, now it will further break down to give this intermediate. So this lone pair will move here, it will form a double bond O. Now oxygen is having a positive charge, and this bond pair will move to the oxygen, and oxygen will have a negative charge. Now further, this bond will again move to give this 2 moles. Okay, so this is a very complex type of mechanism. You don't have to remember it. I'm just giving you it here because children often ask from mechanism, and yes, it is also good for students to practice this mechanism. But you should not be doing it in near the JEE exam. But yeah, it is good. It is a good practice to do the mechanism. Now further, this carbonyl will attack again because it is a nucleophilic center having a oxygen positive charge. Yes, this oxygen is having a positive charge. This carbon will be a good nucleophilic center. Now this carbonyl will attack here, and we will get this kind of structure. So this is a very important structure. This is called ozonoid. Now this ozonoid will be further hydrolyzed. So we will just, depending upon which kind of say workup we are doing. So if you are doing a reductive workup, so it can be also done in the presence of Me2S. Okay, so if you are Me2S, we can do it in the presence of Me2S also. Or if you are having this Zn dust in H2O, you can do it here in the same way. So what will happen? This bond will break Okay, in this fashion it will break, and we will get our 2 moles of this aldehyde or ketone depending upon where the alkene is present. So since it is at you can say at not a terminal alkene, an alkene just below the means just on the left of the terminal carbon, we will get a mole of aldehyde and a mole of ketone. But if we do the oxidative workup, that is this one, then we will get of course a ketone, and plus that the carbon that is having at the last will get at the carboxylic acid here. So this method can also be used for the preparation of carboxylic acid. So this reaction is very you can say important. So if I summarize it in one line, you can say it like this. So if you have an alkene, suppose it can be done in 2 ways. So for reductive, this is the reductive one. This is the oxidative one. We take the O3. For reductive, we can have 2 Zn dust and H2O, or we can have this Me2S. For oxidative, we will have this H2O2 and OH minus. Sorry, let me write it here. H2O2 and OH minus. So this one will give us, suppose it is the hydrogen, and this is R, this is R, and this is also R. So it will break from here. This will give us ketone in this case. Means maximum oxidization takes place without the breaking of carbon. So this carbon can maximum oxidize it to, we can maximum oxidize to the carboxylic acid. So we get a carboxylic acid, which will look like this of course. And this can be maximum oxidized to this ketone. Means we cannot break the CC bond, and until and unless we are not breaking it, we can oxidize it further. Now this one will give us only aldehyde, since it is the reductive one. Plus we'll get a RCHO. So this is the summary of this ozonolysis of alkene. Now next we will see these are the general method from which we can prepare both aldehyde and ketone, you can say, depending upon the nature of alcohol that we are taking. So say first primary, secondary and tertiary. Now we will see some other method which are specific to aldehyde, then we will see some method which are specific to ketones. So first for aldehyde, we can take it from nitrile. So the first reaction is a name reaction, so it is an important one. So it is called a Stephen reaction. So what we do, we take a nitrile, we do it in the presence of SnCl2 and HCl. So this gives us this alkene, sorry, imine, you can say, sorry, imine. Now this imine on hydrolysis will quickly give us this RCHO. Okay, so this is the Stephen reaction. So remember, this reaction is very important. Means the part of this reaction is also very important. This one. So as we introduce and water to this imine, it completely, and you can say quickly, transform into aldehyde. So this is a very important reaction. So if you want a short description of this mechanism, so it happens like this. So this is the NH that we are having. So this H3O plus will give this H, okay. And now the remaining H2O will attack here on this carbon, and it will move the bond to here. Now since we are having this kind of structure, here a single bond instead of double. Since it is having a positive charge, and we know that nitrogen is more electronegative than now this nitrogen will take up this hydrogen from here. It is the interproton transfer, okay. Now this lone pair move like this, and this will leave and give us NH3, okay. And now further it will have a positive charge, which will be again given by this RCHO kind of thing. this will leave as NH3. Okay, now this will be taken up because it is a acid catalyzed reaction. We will get back this H plus. So this is the overall mechanism for Stephan reaction. Now we can also do the reductive thing, oxidative thing using a metal. So here is the thing that we are having. So we take our RCN, then we do it in the presence of water to give our RCHO. Again we can use another CN here, it is nitrile, or we can also use this diol H. So all these three methods, so in these three methods, hydride is used as the reagent. Means this AlH, this hydrogen, is transferred to this nitrile this as H minus, and it is further oxidized using this H2O to give us RCHO. Similarly, this reaction is the same, and also in diol H, which is diisobutyl. So let me write its name, diisobutyl aluminium hydride. So it also have a hydride with it. This hydride is nothing but H minus. So this H minus will attack the center here. Okay, sorry, it is a CHO. Yeah. Now this H minus attacks here. This leaves first, and on the further attack of this H minus, we get this thing. Yeah, sorry for this mistake. So it has a CHO group here. So H minus attacks here, and we get this aldehyde. So this was from nitrile. Now next, let us move to from some of the preparation that are done using hydrocarbons. So here we are having this toluene in the presence of chromyl chloride, chromyl chloride. So we are taking a chromyl chloride in the presence of the solvent, that is CS2, a non-polar solvent. And it happens through a concerted mechanism also. So I'm not giving the descriptive overview of this mechanism. You have to remember it because it is a complex one. Now we get this kind of complex, that is chromium complex. Okay. Now on further hydrolysis of this complex, simply we give the aldehyde. Okay. So this was the using the CrO2Cl2, that is chromyl chloride. We can also do it using the same substrate, that is toluene plus CrO3 plus CH3O, that is it is a acetic anhydride. Okay. Then on further hydrolysis, it will also give benzaldehyde. We can use this reaction also. So this is called as Gutterman-Koch reaction. So it is an important name reaction. So we simply take this benzene here, okay, and then we do it using this. Say we are doing it using this electrophilic aromatic substitution. Okay, so we are taking AlCl3 and CuCl, and we are creating a electrophile, electrophile, which is giving us CHO at this position. So it is nothing but a electrophilic aromatic substitution. Then further we can take the toluene and we can do side chain chlorination. So we know how to do side chain chlorination. So it happens through radical mechanism. The first step is happening through radical mechanism. Now wherever the radical is stable, so of course phenyl radical is not stable at all. So this carbon radical is stable because it is you can say it is resonating all through this benzene ring. So it will give suppose if you have a ring that is extended, then also we will have this radical formation here also, that is Cl will be added here only. Okay, but it will not move further. So we have to have this 2-chlorine for the cause of this H2O, or you can say hydrolysis of this group. So what we do is we take this toluene, we do the side chain chlorination using HNu and Cl2. So we are di-substituting this carbon, 2 chlorines are substituted on this carbon. Then on further hydrolysis at high temperature, we get this benzaldehyde. So these are the methods we can use to form this aldehyde. Okay. Then next we will see some preparation of ketones. So the first one is we are taking a Grignard reagent here, and in the presence of CdCl2 we again get a this kind of thing. Now this Cd is a metal here, that is cadmium. It is having 2 R. Now this both R can act as a nucleophile because this can move like this. So what we do, we take this RTC2. Now one of the R attacks on this nucleophilic center, so it is a very good nucleophilic center, that is acyl chloride. So this one of this R, it moves here and attack here, and this Cl is a good leaving group, so it leaves, and we get a ketone here plus CdCl2. So since this Cd has 2R, so it will substitute one by one this both of this, so means 2 moles of this acyl chloride. So first 1 R will leave and we will get this CdCl. Okay, then another CdCl R, then another R will move and we will get CdCl2. Then we can also do it using this nitriles. So similarly, we are this, remember this thing, that this nitrile is a very good nucleophilic center because it has a delta positive charge. So we will see in the next slide, on the next lecture, that carbonyl is a good nucleophilic center because it is having a polarity. So a nucleophile can, an electrophile can attack here. Similar to that, this nitrile is also a good nucleophilic center. So each and every time you are seeing attack on this carbonyl, this carbon which is attached to three bonds by nitrogen. Now this C6H5 MgBr, this C6 will attack here similarly. We will get this kind of amine. I now have told you earlier that this amine is irresistive to this H3O plus. So as we introduce this H3O plus to this amine, it will quickly hydrolyze and give you this ketone. Okay, so this is a 1-phenyl propanone because this is a propane here, and it is propanone because carbonate is attached here, and at first position we have this phenyl group. Then again we can use simple reaction, that is Friedel-Crafts acylation. So you have studied this electrophilic aromatic substitution type of reaction earlier also. So we do it in the presence of Lewis acid, which is AlCl3, and it is best for the preparation of this ketone. Now if you want a bonus thing here, so further if you want, you can reduce this thing using LiLH4 to get this CH2 R or AR, HOH. Okay, now if this carbon is again having a hydrogen, you can heat it in the presence of an acid, H plus, and heat, and you can get a alkene. Further you can just add this H2 or use the catalytic hydrogenation and you can get alkane. So in this way you can transform this carbonyl, or you can say acyl, into your required product. So it can be also used for the preparation of this benzyl alkyl benzene, other than the Friedel-Crafts alkylation. And this process is also more, you can say, more trusted one. Why? Because during this formation there is no kind of intermediate formation of carbocation, so rearrangement does not take place. So whatever this group you are taking, it will be directly attached to this benzene without any rearrangement. But in case of, if you are doing it in the presence or in like this, that you are taking CH2Cl and you are doing the Friedel-Crafts alkylation, then there is a chance of rearrangement and it is not a trusted one to get your required product at last. So this was all about the preparation of ketone. Now let us see some physical properties here. Okay, so these are the physical properties of this. First we will see the boiling point. Okay, so if we have the butane, then we have the methoxyethane, then we have the propanol, then we have the acetone, then we have the propanol. So these are different things. So first one is a hydrocarbon, of course, hydrocarbon. Second one is a ether. Third one is a aldehyde. fourth one is the ketone, and seventh one is the alcohol. Now this, all these are of comparable molecular mass. Comparable molecular mass. Now, since all of this are of a comparable molecular mass, this is a very good way to compare all this functional group. So keep in mind that if you are comparing something with something, you must have a comparable molecular mass so that you can compare. Okay, this is the functional group, and this is the thing that we are having the differentiation. Okay, so if then this is the molecular mass, you can see very clearly that it is almost comparable. 58, 58, 60, 60. So the maximum deviation is of minus 2. Minus 2 or plus 2, you can say. So maximum deviation is of minus 2 or plus 2. So this is a very good comparison. Now if you see here, this has the maximum. So let me denote with a different one. So this has the maximum boiling point. Why? Because of hydrogen bonding. H bonding. Now moving on to acetone and propanol. Okay, so this acetone is having a slightly greater boiling point. Why? Because if you see the structure of this ketone and aldehyde, so this thing is more polar. So if you say, so mu is greater for this one, that is dipole moment is greater for this one. And why? Because this both are the R here, so they are doing kind of inductive effect plus I effect and increasing the electron density to this oxygen, and we are getting a greater separation of charges. Okay, so due to this reason it is more polar. Now this is a polar, so it will form a dipole. So the dipole interaction in case of acetone is more as compared to this propanol. Now do not get confused with one thing, that yeah, we have a RCHO, it can do a hydrogen bonding with R. So it will never happen. Why? Because the basic criteria for the hydrogen bonding is that this H must be attached to a certain group of atom, which is nitrogen, fluorine and oxygen, and then only it will show the hydrogen bonding, but it is not directly attached to any such atom. It is attached to carbon. So we will not see the hydrogen bonding in propanol also. Okay, now since it is having a lower dipole moment, it is just placed above it. Now coming to methoxyethane and this butane. So methoxyethane is somewhat having a dipole moment, not as high as this propanol, because propanol is having a high dipole moment. You have seen the reason, or the ketone, because we have this double bond, and of course you can have this thing also. So due to this resonance structure, it is highly polar. Carbonyl compounds are highly polar, but methoxymethane is having nothing like that, structure nothing like that. Okay, so it will have a lower, you can say, boiling point as compared to all of this. It is 281. At last we have butane, which is simple alkyl structure, no oxygen, no heteroatoms at all. So it will have the lowest boiling point of all of those. And why is it so? Because it does not have any dipole-dipole interaction, it does not have any hydrogen bonding, it is just having van der Waals forces due to the molecular mass. So this is the comparison of all the boiling point in one. So this is a very good comparison, you can use it for a further reference also. Now next, let us see the solubility case. So if you take the solubility, so the solubility of aldehyde and ketone decreases as the length of the alkyl chain increases. So if you are taking a lower alkyl chain, then of course it will show this higher solubility. So we will see the reason now. Before that, all aldehyde and ketone are fairly soluble in organic solvent. So this was about water, or you can say polar solvent. So if you have organic solvent which is non-polar in nature, so this aldehyde and ketone are fairly soluble in those non-polar solvent. Now one more point, I have a commercial view of this aldehyde and ketone I put up here. So they can be used for perfumes and flavoring reagents also. So because it has a good aroma. Okay, so this can be used for perfumes and flavoring agents. Now, what is the reason behind this solubility of aldehyde in ketone? So the reason is hydrogen bonding. So simply it is due to hydrogen bonding. Now, students, this is a point I want to make here. So do not use it everywhere, this hydrogen bonding, but of course this hydrogen bonding in organic is very important. In organic, in inorganic both, but for organic it is mostly important because it explains most of the phenomena. So if you look at every chapter in NCRT or any other book, you will see that in every chapter there is a certain application of this hydrogen bonding. So you should be aware about this hydrogen bonding. Okay, so it is very important for your JEE exams. So in many cases, acidity, basicity, boiling point, and many other phenomena are explained using this hydrogen bonding. So since this water molecule is having a hydrogen, it is attached to electronegative oxygen. Okay, so this will form a hydrogen bonding with carbonyl oxygen, which is highly polar in nature, that is having a greater negative charge. So it will form a hydrogen bonding, and of course it is more say soluble than ether, because ether is having a lower polarity. So oxygen is having a less negative charge on it as compared to this carbonyl, which is having a higher negative charge on it. So it will form the hydrogen bonding. Now as the length of this alkyl chain increases, this polarity decreases, and we see that, okay, that we are having a greater you can say a greater at boiling point. Okay, sorry, a smaller boiling, a smaller solubility. Now one thing I want to mention here is that this difference in this solubility is not due to the higher polarity of this propanol, this acetone, because aldehyde, okay, sorry for this confusion, aldehyde is having greater polarity, because this R is somewhat neutralizing this delta positive charge by plus I effect. So of course this aldehyde will have the greater polarity. Now why is this change? Because the reason is very simple. So if you see this if we see this area here, so what is the structure of this propanol? So it will look like this, and if you see the structure of this ketone, acetone, which is CH3. This is the structure of both of this. Now it is mainly due to a greater surface area. Okay, so this is a very typical thing. I have not gone in depth, but yes, due to the surface area, it is having a greater van der Waal, you can say van der Waal forces, due to which it is having a acetone is having a greater surface, a greater boiling point. So you should keep in mind that it will never happen that aldehyde will have a lesser dipole moment, ketone will have a lesser one. Okay, so you should not get confused with it. Sorry for the confusion. Now let us move to some questions. So here is a transformation that we are having here. The most suitable region for this conversion is, so we have to stop it at aldehyde. So I have told you earlier also, so if you have to stop it at aldehyde, you should have a mild reducing agent, which is absolutely PCC. Okay, so the same thing is written here, that we are pyridinium chlorochromate is the mild oxidizing agent which causes conversion of alcohol to aldehyde stage, while other causes conversion into acid. Now next, in Rosenbund reaction, so I have not taught you Rosenbund reaction because I thought it that I will directly say you here only. Okay, so what is the Rosenbund reaction? So this is the Rosenbund reaction. We are taking a acyl chloride, so this R can be AR or allylic, sorry, allylic saying or aliphatic chain, both. Normal alkyl group, or you can say straight chain. Then in both cases, this acyl chloride will be reduced to this, sorry, oxidized to this RCHO, H2PdBSO4. Okay, so why is this BSO4 used? So it is used to remove, sorry, to deactivate palladium. Okay, so this is used for deactivating palladium plus HCl. So this is a fact you should remember. Okay. Now next, the formation of aldehyde from alkyl cyanide. So what we are taking? RCN to this. Aldehyde is related with the name. So we have seen this reaction, Stephen reaction. If we are taking the nitrile and we are converting it to aldehyde. Okay. Now next. So this is the thing that is same thing written here. So we are getting imine chloride, sorry, RCH, and as we introduce water, we get this aldehyde quickly. Now next, formaldehyde is a planar molecule, one, and it contains sp2 hybridized carbon. So this is a session reason type of question. So both are of this correct because we know very well that this is the structure of formaldehyde, and of course it is planar because this carbon is sp2 hybridized and no other sp3 carbon is present. Now next, this is sp2 hybridized. So this is the reason only it is planar in nature. So both A and R are true and R is the correct explanation of the same. So this is the correct answer, first one. Okay. So it is correctly written. Now next, which of the following compound is formed when benzyl alcohol is oxidized with KMnO4? So I have another reaction here. So whatever chain we have, CH2, CH3, any chain, any alkyl chain that we are having here. So as we use this KMnO4, and it is a very strong reducing agent, so it can oxidize this quickly into COOH, that is benzoic acid. So this is an important reaction. So this KMnO4 can convert the benzene with any length of alkyl chain to this benzoic acid. So this is the correct answer. Now I have solved 5 questions. Now I will slowly show you 5 questions. You can solve it by yourself. If it is difficult, I will give you some hints. So this is the answer that is written. Ozonolysis of buta 1,3-diene. So we have this butane 1,3-diene. What will it give? So two products are possible. So you can do it by yourself. I'm not doing it right now. So this is the ozonolysis. Sorry for this. It is just HCHO plus glycol plus CH3 CHO. So this is the option. So it is not encrypted properly. So it is written HCHO plus glycol plus CH3 CHO. Now next we have this reaction CH3 CH2 and we are having a nitrile group. So I have told you earlier that this CN is nothing but a nucleophilic center. So this HMGBr is having a phenyl as electrophile. So it will attack here this nitrile group. Again we will do the hydrolysis and that imine group will be removed and we will have a aldehyde. Then we will introduce another mole of PHMGBr. Then similarly it will be just forming a kind of alcohol, and this is the overall reaction. Now you have to say that whether the product that we are having is symmetrical, unsymmetrical, or you can say both unsymmetrical and symmetrical product, means two products are possible, or no reaction. So this is the question number 7. Now on 8th, which of the following will fail to react with potassium dichromate? Potassium dichromate and dilute sulfuric acid. So we have 4 cases: ethanol, propanol, and each of this. So I have told you earlier that only KMnO4 at elevated temperature can break CC bond, and other than that I have told you no reagent that can do this. So you just have to find that means option that requires oxidation to cleave one CC bond. That is all about this question. So I have put only 4 questions here. Sorry, 3 questions here. Okay, so we will do next in the next class. We will see the reactivity of this carbonyl. So that is the most important one you can say on this aldehyde, ketone, and carboxylic acid. So thank you for your time. So if you have any question, you can ask right now. जा रहे हैं